So we're going to follow the same process of estimating a population, but with a mean. So instead of working with proportions now, we're going to work with a mean. So we'll find the point estimate for that mean, construct confidence intervals, find sample size, but we also have to talk about this student t distribution. So starting with obtaining a point estimate. Remembering that a point estimate is the value of the statistic that we use to estimate the value of the parameter. So the sample mean, the statistic, is going to be used as the point estimate for the population mean parameter mu. So in the following example, it says the website fueleconomy.gov allows drivers to report the miles per gallon for their vehicle. The data in table 2 shows the reported miles per gallon of 2014 Toyota Camry automobiles for 16 different owners. Obtain a point estimate of the population mean miles per gallon of the 2014 Toyota Camry. So we want to estimate the population mean by calculating the sample mean. Sample mean is something that we calculated back in chapter 3. The sample mean is found by summing all of these values together, find their sum, and divide by how many values there are. So we'll find the sum and then divide by 16. Okay, so if you are to calculate the sum of all 16 values, you should get 449.6. If you divide that by 16, you will get 28.1 miles per gallon. So what does that mean? That means our sample mean is 28.1 miles per gallon, and we are going to use that to be our estimate of our population mean. And we know from last chapter, or from last section, that we will then create an interval, which then gives us much more accurate representation of where it could fall. Before we get into that, though, we have to talk about what is called a t-distribution. So suppose a simple random sample of size n is taken from a population that follows a normal distribution. The t-distribution is going to be calculated as follows. The sample mean minus the population mean divided by the sample standard deviation divided by the square root of the sample size. Okay, this down here is an estimate of the standard deviation. So we are taking this data value in question minus the mean, all divided by our standard deviation estimate. And what we're going to do is we're going to graph that with what is called n-1 degrees of freedom. Now, to understand what that means, I'm going to give you an example here. So consider that I have 5 pens of different colors and 5 students that want to borrow a pen. The first student has a choice in what they pick, as does the second, third, and fourth. So the first 4 students that come up to my desk to borrow a pen have a choice or have freedom of choice to which pen they select. However, that last student does not have any freedom. Okay, so what we do is we say our degrees of freedom is 1 less than the sample size because it takes into account how many actually have a choice in this situation. Okay, so what makes this different than a normal curve is that we are basing it off of our sample size here. And we are also basing it off of a sample standard deviation. A Z curve has a population mean and a population standard deviation. The T we are using to estimate based on a sample standard deviation. So what I'm going to do here is I'm going to show you the difference between the Z spread and a T spread taking 2,000 random samples of size 5 from a population with a mean of 50 and a standard deviation of 10. So I'm going to take a sample of 5, calculate the mean and standard deviation. Sample of 5, mean standard deviation. Repeat that 2,000 times, looking at both the Z and the T. Just to show you here, the only difference between the two is Z uses population standard deviation and S uses sample standard deviation. Okay, so let's look at the first one here. We're going to use technology here. You'll see the screens on the next page. Again, filling in what we know. Our population mean is 50, standard deviation is 10. Our population mean is 50, and this one we're going to use our sample standard deviation. This one changes for every single sample we look at. This first one here is the Z, or the normal distribution that we are used to. The second one over here is the T distribution. So if you look at them, they clearly are different. Here's what I see. They both center at 0. But in this normal curve, I go from -3 to +3. Okay, and that's familiar. We go 3 standard deviations left, 3 standard deviations to the right. But if you look at this T graph, we have all the way down to -10 and up to 7.5. So this graph has a lot more spread than the first graph does. And that's really what is stated on this page right here. So that first graph goes from -3 to 3. It's symmetric. It looks like our normal curve. But our T has those longer tails. Okay, this tail is really long before I peak and really long. So the peak part is a lot more narrow, but then I've got these really long tails in my T curve. This is due to the fact that we base our information on the sample standard deviation and not a population. So every single one I draw, this is different. We're in a Z-curve. This is standard across the board. All right, so I'm going to repeat this now with samples of size 10. So I take sample size 10, sample size 10. Repeat that 2,000 times, and let's see what happens. Again, they're centered around 0. This one still goes roughly -3 to 3. But now look at T. T is looking a little more like that Z curve. It is looking a little better. I go a little past -0.45 and about up to 4.5. Sorry, -4.5 to +4.5. So it's getting closer, but it's still not quite there. And again, same wording here if you want to read it. Biggest thing we need to look at is that even though we're working with the same sample size, and even though it may be less dispersed, it's still different. And if I look and just compare the two T graphs, this T graph sample size is different than the T graph back here. Different. Whereas the normal curve still goes from -3 to 3. That one did not change. So the normal curve is standard. It's always going to follow that. T is dependent upon your sample size. It is going to change shapes for different samples. As I increase my sample size, the spread will become more narrow. and then it will behave more and more like a normal distribution. Let's discuss the t-distribution. So first off, we use the t-distribution here when we have sample standard deviations, when we don't know that population standard deviation, or when our sample size is small. So we use the t-distribution because it allows us to differentiate based on our sample size, which then determines our degrees of freedom. It is still centered about 0. It is symmetric about 0. That is no different than the normal curve. The area under the curve is still 1. Half and half, if you split it from 0, that is still all the same. The graph increases or decreases without bound. It will always go closer and closer to the x-axis, but never actually touch it. The area and the tails of the t-distribution is a little greater than in a normal curve, just because we are using the standard deviation sample as an estimate of the population. Because we don't know the population, we have a little more spread here. Remember that as the sample size increases, the curve is going to get closer and closer to normal. It's going to eventually kind of follow that same thing around that 30 mark, like the central limit theorem says, is roughly going to be where the t kind of meets the z curve. So you can take a look here. The blue is the normal curve. This pink is samples of size 15. And the orange is samples of size 5. So the smaller your sample size, the shorter the peak and the longer the tails. But again, as I increase those sample sizes, it is going to get closer and closer to the shape of a normal curve. Just like we determined z values, we can determine t values. So we used the notation before, z alpha, to represent the z-score, whose area under the curve to the right of z is alpha. So we can do the same thing with a t-distribution and find t alpha, finding the value of the area to the right of that score. We'll also do to the left and between, just like we did in our normal curve. One option that we have that we can use here is these tables. Now, I rarely show you the tables because a lot of times they're more confusing than they need to be. But I'll show you really quick here, and then after that, I will show you how to do it in Stack Ranch. So find the t-value such that the area under the t-distribution, the right of the t, is 0.10. Assuming 15 degrees of freedom, that is, find t sub 10, 0.10 with 15 degrees of freedom. So a lot of times what we like to do is we draw ourselves a graph. So our t-distribution has a mean of 0. We want to find t 0.10, so the area to the right is 0.10. I want to know what value gives me this area. This, again, is a portion of a table. This table is in the back of your textbook. You can find it online. It is a standard table that is used for all t-distributions. Okay, so what I can do here is I find the area that I want, 0.10. Area in the right tail, so 0.10. And then what I'm going to do is I'm going to locate my degrees of freedom that I want, 15. And find where the two intersect. So right here, 1.341. So the t-value of 1.341 is going to give me a right area of 0.10 when I have 15 degrees of freedom. That is what that means. And I believe I have that listed right there. So let me clear my ink here. The value of t sub 10 with 15 degrees of freedom is at 1.341. That is the area under the t distribution to the right of t of 1.341 with 15 degrees of freedom is 0.10. To compare a z, normal z, so normal curve, area to the right of 0.10 is 1.28. There's a slight difference here. 1.34 is a little further out, showing me that spread, versus my normal curve would be at 1.28. Just know that, again, anytime we are working here with these means, these small sample sizes with means, or using the sample standard deviation as an estimate, we are going to be using this t distribution. Okay, so really quick, how do we do these in Crunch? It's going to be just like we did in chapter 9 with the normal curve, except that we're going to use the t-curve. Stat calculator. All we were doing before was normal, so I'm going to instead go to t because it says find the t value. Degrees of freedom is going to tell me that I have 19 degrees of freedom, and I have area in the right tail is 0.02. And the right tail means I want greater than. I'm going to shade to the right. You can see that there. The value I have shaded to the right. The t-score is 2.20. Okay, we can do the next one. So 6 degrees of freedom. And the easy way to remember, left, less, left, less. So when I see this one, left is always a less than symbol. That's how I always remember left, less. Left. We want left. Degrees of freedom is 6. And the area to be 0.05. Okay, this one is negative 1.94. All right, and then last one is a between. So the area creates a 95% confidence with 16 degrees of freedom. I'm going to click between. We have 16 degrees of freedom, and I want the area to be between them to be 0.95. And just like a normal curve, these again will be the exact same values, one positive, one negative. So negative, positive, 2.12. Positive or negative 2.12. We had to discuss this because this is the distribution we will use when we do confidence intervals for a mean. As we construct confidence intervals for our mean, remember the following, that it is random sampling. The sample size should be less than 5% of the entire population, which will happen. Okay, again, every question I give you, these initial conditions are going to be satisfied so that we can just conduct the problem. The data comes from a population that is normally distributed or the sample size is large. So here is what it looks like in equation form. You take the sample mean, aka the point estimate, add and subtract your error, which is found by taking your score times your sample standard deviation, divided by the square root of the sample size. Remember that we don't use the formulas here, but just to reiterate that we also look at this as the point estimate plus the margin of error. So that second part, the T alpha over 2 times S over square root N is the margin of error. So it is still point estimate plus and minus margin of error. Okay. The only difference here is we are now using a mean and a T value to get our margin of error. We do need to look at what is called the normality condition. When Gossett developed the T distribution, he assumed the sample data came from a population that is normally distributed. Most distributions are not exactly normal, so we should always verify that our data appears normal enough before using our T distribution to conduct our tests and to make our confidence intervals. For this class, all questions posed will be able to work. So again, we will not worry about this step. Kind of like I said before, the sample sizes will always be less than 5% of your population, okay? All of those things will already be true, so we can just do the math. I'm gonna go back to that Toyota Camry data, and we had 16 values of data. Now here, you're hearing me say data, data, data. So anytime we run these tests, we have the option of using a summary or data. So this first one we're gonna do, we need to copy our values into StatCrunch. 25.9, 26.2, 32.5, 32.0, 27.2, 30.0, 25.5, 26.4, 27.4, 27.4, 27.0, 28.0, 31.2, 25.1, 30.6, and 27.2. Reading is key here. We want to construct a confidence interval on the mean. Anytime we are doing a mean test, we are going to go to stat, P stats, okay? Anytime we do proportions, we go to proportion stats. So for chapter 9, chapter 10, chapter 11, these are where we are going. Proportion stats or T stats. T is for means. We are going to do one sample, and just like before, we have data or summary. This one is data. So I'm going to click my data and click that I want to create a confidence interval. Okay, it is going to give me my confidence interval here, which I have on my next slide. 26.832 to 29.368. Here's my sample mean of 28.1. And we use that to give us the range of values where we expect the population mean miles per gallon. If I were to have access to the whole population for a 2014 Toyota Camry, should be between 26.832 and 29.368 miles per gallon. 95% confident in that result. The lower bound 26.83, upper bound 29.37, which means we are 95% confident that the mean miles per gallon of all 2014 Toyota Camry cars is between those two values, 26.83 and 29.37 miles per gallon. We are using our sample value to create a range of values where we expect the population value to fall. Okay, that is the whole goal of this. being able to take my sample information and say, where would the population value be? The following data represents the amount spent on Valentine's Day among males who purchased gifts for the holiday. The data is based on reports from fundevo.com. Construct a 90% confidence interval for the mean amount spent on Valentine's Day among males who purchased gifts for the holiday. Okay, so note that this is only specific to those who spend money. So if you said you don't spend money, you are not used in the creation of this study. V-Day is what I'm going to call this. And I'm going to enter my values. I've got 216, 146, 156, 120, 125, 189, 133, 201, 229, 137, 150, what is that? 155 and 262. Okay, I want to run statistics based on a sample that is small with means. So I'm going to go to T-stats, one sample, and again, I have VTEP. All right, so this time I'm using Valentine's Day, and I want to make a 90% confidence interval. We are dealing with it money here, so I'm going to go to 2 decimal places. So we have 148.6 to 196.27. That is my confidence interval. So if I want to interpret that, we are 90% confident the mean amount spent on V-Day among all males who purchase gifts for the holiday is between $148.56 and $196.27. So we are fill in the blank confident, you're looking for here, amount spent on Valentine's Day among males who purchase gifts for the holiday. And this, when we create our statement, we add the word all males because we are now referring to the population mean. You could have also said, instead of putting all there, you could write it as, we are 90% confident that the population mean amount spent on V-Day among, and then you wouldn't need all there. So you have, there's a little bit of different way you can write the sentence. Just make sure that it makes sense and that you have included your level of confidence, the parameter in question, mean, proportion. Eventually we'll talk about standard deviations here, what it is that you're looking at, and then what it is actually between here. Based on a random sample of 40 online orders at Giuseppe's Pizza, a 95% confidence interval for the mean amount of the order in dollars has a lower bound of $21.09 and an upper bound of $29.59. What is the point estimate and what is the margin of error? This one is asking us to work backwards. We have the lower bound of 21.09 and the upper bound of 29.59. We know that the point estimate should be in the exact middle of these two values. The way we find that is by finding their average. So I open up a calculator here. 21.09 plus 29.59. I'm going to add the two values together. And then I'm going to take that result and divide by 2. That is going to give me the exact middle. So the exact middle is the point estimate. So our point estimate was 25.34. Exact middle, calculate the average. A margin of error is how far middle is from one of your ends. So 21.09, then I have 25.34, and then I have 29.59. You're looking for the difference between these two. And the answer should be the same for each pair. So it doesn't matter which pair you work with, as long as you just pick one of them. If I want to find the difference between the lower and the middle, so 25.34 minus 21.09. $4.25. So let's see if that's the same for the other one. 29.59 minus 25.34 is also a difference of 4.25. You can always work backwards. If they give you the interval, you can work backwards to find the point estimate and the margin of error. I also want to show you really quickly, you may come across a problem where you would use summary. Let me show you what that one looks like here. So T1 sample summary. Okay, this one is asking for your sample mean, sample standard deviation, and sample size. Let's say, I grab an example here really quick. A simple random sample of size n is drawn. The sample mean is found to be 35.1. So 35.1. With a sample standard deviation of 8.7. Construct a 90% confidence interval if the sample size is 40. Okay, so sample size is 40, and then you construct your confidence interval down here. If they specifically tell you what the mean, standard deviation, and sample size are, you're going to use summary instead of data. Okay, data is when we have all the raw values that we type in. So it's going to look the same in the answers, and you just look at lower limit, upper limit. Tootsie Pop is a sucker with a candy center. A famous commercial for Tootsie Pops once asked, how many licks to the center? How many licks does it take to get to the center of a Tootsie Roll of a Tootsie Pop? I forget exactly how it's phrased, but it was something a little longer than what's listed here. In an attempt to answer this question, Corey Heed of Siena Heights University asked 92 volunteers to count the number of licks required before reaching the chocolate center. The mean number of licks was 356.1. So mean 356.1. And the standard deviation was 185.7. Find and interpret a 95% confidence interval. You determine the number of licks required to reach the Tootsie Roll center of a Tootsie Pop. I believe that's how it was said. How many licks does it take to get to the Tootsie Roll center of a Tootsie Pop? This one's going to be like what I just showed you, using summary. Stat, C, because we're working with means, one sample with summary. So 356.1, 185.7. Sample size was, I think there were 92 students. Yes, 92. And we want to conduct a 95% confidence interval. 317.6 is probably going to make more sense to think about this in whole numbers, but 317.6 to 394.6. Okay, we're gonna skip that one. So we are 95% confident the mean number of licks to reach the center of all Tootsie Pops is between 317.6 and 394.6. Makes a little more sense to say between 318 and 395. So if you said that, that would, I mean, makes a little more sense. I can't take part of a lick. So 318 to 395, if you round it to a whole number, to me, that makes a little more logical sense. But given that our original values had a decimal, you could leave a decimal there. Okay. Number 30 is just another same type of thing with a summary. If you want me to do it in a later video, I can always do it later. Just ask if you want an extra example. Last thing then is our sample size. So just like we determined a sample size with proportions, we can determine the sample size we need for estimating a population mean. Okay, this formula is a little simpler. It is just n equals the z-score times the standard deviation, all divided by the error, then squared. Again, I will always show you the formulas. If you want to do this by hand, you can, but I will also show you how to do this in StatCrunch. You may be asking yourself though, hey, wait a minute, why are we using Z? When we do this formula, we will use the z-scores. Z-scores from that table, z-scores from that table. We did 0.90, 0.95, and 0.99, I believe, were the three that were in the table. Back on slide 20. To do this by hand, you have to either have that slide close by or you have these values memorized. 1.645, 1.96, and 0.575. They're going to default to use those values because they're standard across the board. And because we don't know our sample size, we can't figure out a degrees of freedom. So we have to be able to just use our Z values. Let's consider again the problem of estimating the miles per gallon in that 2014 Toyota Camry. How large of a sample is required to estimate the mean miles per gallon within 0.5 miles per gallon and a 95% level of confidence? So in order to do this, we would need the values of Z, S, and E. So Z comes from the table. 95 would be 1.96. You would have your sample standard deviation, which was 2.38, and the error is 0.5. Now, notice, this does not change here. Anytime we work with means, this is the error. When you work with proportions and they say the error is 2%, 2% goes in as 0.02. So please just make sure you are reading these things correctly. And this, when you're working with means, does not change here. This is not a percent value. It does not change. It is literally half a mile per gallon. Okay. Again, this is one way to do it. If you want to do it by hand, that's fine, but it always leads to some potential error. So instead, where I like to go is in StatCrunch. We are still working with means, so we are still in T-stats. We are still using one sample, and we're doing a width sample size. We want a 95% confidence with a standard deviation of 0.38 And our width, remember, is double what they give us, double the error. Double a half makes 1. So width is always double the error. This one is telling me my answer is 90. So again, remember that technology and by hand using some rounding is going to be slightly different. So this one rounded would be 88 because we round up. Technology gave us 90. Remember that width is 2 times the error. So we put in 1. Dr. Paul wants to estimate the mean serum HDL cholesterol of all 20 to 29-year-old females. How many subjects are needed to estimate the mean serum HDL of all these females within 2 points? So 2 points equals the error with a 99% confidence using S is 13.4. Okay, so that's the first part. That's what we want to do. Confidence level is 99%. Standard deviation is 13.4. And the width is double the error. So the width is, or so the error is 2 points. So I double that for 4. Sample size is 302. Okay, by technology. If you wanted to do it by hand, you are going to use 2.575. 2.575 times standard deviation all over the error, quantity squared. Okay, so I can go here. I'm just going to show you both in case you want to try. Open parentheses, 2.575 times 13.4 all over 2. That should be fine. Hold on. I want the top. I want to make a single fraction. Let me add another pair here. All over 2. There we go. Then go out and square it. In this one, it would give me 298. So there is a slight discrepancy again. It is okay. There will be leeway in the Pearson homework. There is always a little bit of plus or minus that you have for when you're doing those. There's also a little bit of leeway when you're doing them on my test. I prefer to use the StatCrunch just because it's a little more user-friendly. All right, so the second half of this, suppose that he wants to instead do a 95% confidence interval. How does this affect the sample size? If I go back to my, and I change this to 95%, and again, make this 4. And this is why this value is a little different, because the program is rounding to get you as close to a whole number as possible. So this is why this is a little different than by hand. So this one is 175 by the tech. And if you wanted to instead do by hand, to show you here, 1.96 times 13.4 all over 2 quantity squared. This one I don't mind doing by hand as much because it's not as bad as the other one, but the proportion one's really messy. 1.96 times 13.4 all over 2, arrow over quantity squared. So by hand, we got 173. Just again, either of those answers would be acceptable in both the homework and on a test. So in the end, how does decreasing the confidence affect your sample size? Well, if we decrease confidence, the sample size also decreased. Okay, if I don't want to be as confident, I don't need to sample as many people. It's also why if I sample a lot of people, I can be more confident in my results. Those two things go hand in hand. I'm going to tag on here really quick this 9.3 section because it's like one slide. How do you know which one to use? Because we've now discussed two types of them. Right now, we've done proportions and means. So anytime you do a proportion, as long as this condition is satisfied, we are going to use our proportion stats, which utilizes z-scores, also known as the normal curve. Next one. If we are doing means, if the sample is greater than 30, is it greater than 30? If the answer is yes, we just default to our t stats. That's where we go. If it is not greater than 30, we always have to check to say, does it come from a normal population? We will always have that happen. We are not going to work with anything that does not come from a normal curve, normal distribution. You don't need to worry about that. In the end, any mean, we are using our t-stats. So if it's greater than 30, t-stats. If it's less than 30, we are going to assume that it is normal and can still use the t-stats. All right. The last section that we are going to work with, we are only going to hit on standard deviation here. Standard deviation and variance are going to go together. This is going to be the last section that we cover in my next video.